All right. Now we generalize it with the notation of probability, as I showed you previous slide, and also think about the best response of each part E in this case. But let's first just write, just have the, how you call it, normal form up again. So you would have something like this, a matrix, 2 times 2, right? You know, I cannot draw straight to there because I'm exhausted a little bit. So here, let's say for the husband, and here is for the wife on the vertical. Now, you have Bartlett and Bartlett. Let's write it a bit higher. So the pair up is 2, 1. Here's boxing. The pair up is 0 for both. And you have here boxing for the wife. The pair up is 0. Here, if they go for different activities, right? And 1 and 2 if she goes to go boxing with her husband. I write down the probability again. So the wife will go for Bartlett with probability W and boxing with 1 minus W. I said that right. And similarly for the husband, that will be H for Bartlett and 1 minus H for boxing. That's what we have. Put it in a bracket though. Okay. Now let's see the wife's expected payoff. Expected payoff for the wife, which is EW. I will abbreviate the payoff now just to save space and time. Now, so EW equals, by the way, normally E is for expected, the expectation notation, equals, again, the probability of each scenario times her certain payoff in the certainty case. So W, probability that she plays Bartlett, times H for the probability that her husband also go for Bartlett, times payoff 2, right? Plus, now move to the next. The probability that she play Bartlett, but her husband, now she plays, it's a confusing thing here. Plays, I mean playing the strategy, not the activity itself. No. And then 1 minus H if her husband goes for boxing, times 0. No. Let's make again the border over here so I don't mess them up. It's like a thought in your head now. Plus, the next scenario, she wants to go for boxing, 1 minus W, and then her husband wants to go for Bartlett, so but that's true, H times 0. Plus, the next thing is the probability that she and her husband both go to C boxing together, so that probability will be 1 minus W times 1 minus H, right? And times her pair in the certain case is 1. Now, simplify things. So you have two terms times 0 in between. That's good. We don't have to care about that because they 0 anyway. So that will be the first term over here. Will be 2WH, right? Plus, now this one times 1. So something times 1 is itself, we can ignore it and open the bracket. Just focus on the product of these two probabilities. So 1 minus W times 1, you could rewrite already 1 minus W. And the next thing is 1 minus W times minus H, right? So 1 times minus H is minus H. And then minus W times minus H, which is plus WH, right? And then at the end we could simplify further. 2WH plus 1WH is 3WH plus, convenient later, minus W plus 1 minus H. You will see in a moment why I want to write minus W there. And factor out the W's. So you would have in the bracket 3H minus 1 times W plus 1 minus H. And this is the expected payoff of the wife. One thing would be helpful to realize at this stage is, in a game, players wish to maximize their payouts, right? That's the rational motivation. So, in the mixed strategies version, they wish to maximize their expected payout. So the task for the wife is to choose the probability distribution between the two possible actions so that her expected payoff will be maximized when she randomizes. This is her expected payoff function. So you could already think about maximization a bit in your head. So let's write it here. The first order condition of this maximization problem is the derivative of the expected payoff of the y with respect to her probability, because that's what she could have influence on. Equals, where's W? W is right here. I should have written it in a different color. Okay. That is here is 3H minus 1, right? Because you only have W over here. Okay? Equals 0, meaning the probability that the husband plays ballast would be 1/3, right? And this is one thing to think about, but let's put it there. Forward. But normally you think about it, you usually would solve for W. What you're interested in W, but now you have no W here anymore. So what to do? we could put it back into this expected payoff function again to see what happens for the case that h equals 1/3, sorry, and the cases where it's not. Now, so if h equals 1/3, then EW will be 1/3. So the terms in the bracket is 0, right? And as a result, the first term, 3h minus 1 times w equals 0. Don't have to care about that. So what we have is 1 minus h, which is 1/3 now, equals 2/3. What can you see from this? You can see that it's constant. So the expected payoff of the wife when the probability that the husband plays ballot is 1/3 is constant. So it doesn't depend on which probability she chose for her own activity, right? And in that case, we say the wife is indifferent. Between ballot and boxing. Doesn't matter, no matter what she chose, the expected payout will be a constant of 2/3 when the probability that the husband votes for ballot is 1/3. That's the first thing. Now, what if h smaller than 1/3? I need this term, so I write it here again. E dot E W equal 3h minus 1 times W plus 1 minus h. So one thing to realize here is 1 minus h is larger or equals 0. Why? Because h is a probability. By construction, its value must fall somewhere in between 0 and 1, right? So this term will not be negative anyhow. Go back to the first term. So the wife expected, the probability is also the same, somewhere in between 0 and 1, positive. So consequently, how large the payoff of the wife will depend on the term in the bracket, which is 3h minus 1, right? Let's say, so when h is smaller than 1/3, then 3h minus 1 will be smaller than 0, negative. So you have a negative term plus a positive term. And because the slope of this expected payoff function is negative, the more you increase W, the less payoff you will get, right? the larger W is, the smaller EW is. Consequently, if you were the wife, or if I were the wife, I would choose as small as possible. This is what written on the slide. I'm explaining to you why is the case. Now, choose W as small as possible. And where's W? So I just said W falls between 0 and 1. So the smallest value it could get is 0, right? And what does that mean when she set her probability of playing valid to be 0? She goes for boxing, right? So then we have already one case. If the husband, the probability that he goes for valid is smaller than 1/3, she should choose her probability for going to the same activity, the valid, as small as possible, so 0. And that means she should go for boxing, which is intuitive, right? I mean, if you kind of somehow in the background see that, okay, your spouse had a tendency to go to boxing already, and you want to randomize, then maybe you have a chance to get payoff by going to boxing rather than valid. Similar to last week, right? On the other way around, similar reasoning apply for when H is larger than 1/3. Yeah? Then you would have she or her to set as large as possible. And as large as possible means equal 1, because can't get larger than that. And that means she should go for valid. Now, again, why? Because in that case, when H is larger than 1/3, then this term, the 3H minus 1, will be larger than 0. And when you have the slope of a function is larger than 0, that what does it mean? That means the larger you get, the W is, the larger the expected payoff is. So for that you would like to set W as large as possible. And this explains what written on your slide. Okay, now let's move on to the husband. Calculate his expected payoff. Now, H equals, again, the probability of each scenario, the first one here, W times H times his payoff is 1. No? This marker doesn't work well. Okay. W times H times 1. Now, plus W times 1 minus H, this here, W times 1 minus H times 0, plus here, 1 minus W times H times 0 again, and then plus the last one, 1 minus W times 1 minus H times 2 when it's boxing, right? Oops. Then you have here 1 WH plus 0, 0, ignore it. And then here you have 2. So you write 2 in before and the same thing happens. 1 minus W minus H and then plus WH, right? Simplified. So here 1 WH in the bracket 1 WH but times 2, so that is 3 WH, right? Plus 2 times 1, 2, minus 2W, minus 2H, right? As before I factor out now the H, because we're talking about a husband. So we would have 3W minus 2, right? Times H plus 2 minus 2W. And this is the expected payout of the husband. For him to choose the best response, as before, we only focus on the thing inside the bracket, because it's the slope of his best response function now, right? So this term will be 0 when W equals 2/3, right? So means when the white play ballot with the probability 2/3. And applying the same reasoning before, we know that if W equals 2/3, then he is indifferent. So he could play either strategy. If W now smaller than 2/3, the same reasoning applied, because if it's smaller than 2/3, the term inside will be negative. So he should set his probability of going for ballot as small as possible, which is 0, right? So play ballot. On the other hand, if W is larger than 2/3, then he should set H as large as possible, meaning set it to 1, the upper bound. So to play, sorry, I think I wrote it wrong here. It's actually when H is equal to 0, that is boxing, right? And here's ballot when you set H equal 1. So that's his best response in this case. The first thing we have to remember when we try to find a natural equilibrium is the Nash equilibrium are where both players or all players jointly have their best response to all the strategies played by the other players. So in this case, the husband and the wife must have their best response at the equilibrium, and the easiest way to show And to find this equilibrium, if there's only one, is to use a graph. Now, so batch response is something concerning the two probability. We could put them on two edges of the graph. So let's say this is H, the probability for playing ballot of the husband, and here's W for the wife. And we have 1/3, 2/3, and 1. Similar. So here is 1/3, 2/3, and 1. Now, and remember what we find about the batch response of the wife and the husband. Let's think about our wife first. So for the wife, remember when H, or the probability that the husband will go for ballot, is smaller than 1/3, then she should choose her probability for that as small as possible, right? And that is 0, right? So she would play boxing if the probability that he would go for ballot is smaller than 1/3, and that is W equal to 0 as long as H smaller than 1/3. And where's 0? For her, W is right here, right? So long as H is smaller than 1/3, then her probability is always 0. That's the first thing. The second thing, when H is larger than 1/3, then she will set her probability for going to ballot, W, as large as possible, which is 1. Now, so here 1, but let's first kind of navigate it a bit. Okay. So starting from here, at this part, she will set it as large as possible. Always 1 when H is larger than 1/3. And how about 1/3? Exactly at 1/3. What happened? She's indifferent, right? So she could choose any probability for each strategy between 0 and 1. So this is her batch response function, contingent on the probability, the H from the husband, right? Similar, we turn to the husband. Remember, when the W is smaller than 2/3, he would set H as small as possible, which is 0. 0 is right here, right? Like for the whole range of W smaller than 2/3. So this is the first part of his batch response. On the other hand, when the wife probability is larger than 2/3, what happened? He set his probabilities at as high as possible, right? So on the range where W is larger than 2/3, H is 1, the second part. And similar, when W is 2/3, And he's indifferent, meaning H could fall in any value between 0 and 1 without changing his expected payoff. So that is the best response function of the husband. And this is wife. Because Nash equilibrium is where the best response joined together, we have 3 points. The first point is right at 0. Now, the second point is W equals 2/3 and H 1/3. And the last point is both equals 1. So we have 3 Nash equilibrium. First one, W equals 0, H equals 0. Both plays boxing. The second one, W equals 2/3, H 1/3. So this is when the wife randomized her choice with probability of boxing 2/3. And the husband randomized for ballot, not for boxing. And the husband randomized for ballot with the probability 1/3. And the last one is both equal 1. And then both plays ballot. A final thing about the mixed strategy is, even though, like we seen last week, it does not guarantee that there will be a Nash equilibrium always in a pure strategy set up, for example, the rock, paper, scissors. However, it does guarantee that even when a pure strategy Nash equilibrium does not exist, then a mixed strategy one will exist. Now, and do you know why it's called Nash equilibrium? Because the concept was developed by Nash, the Nobel winner in economics, for his contribution to game theories. It is actually, there's a film about him, it's called A Beautiful Mind. I think some of you may have watched it already. If not, could also be something for your semester break in next month now, after this time. So this statement is was proven by Nash about the existence of an equilibrium in all finite games. So what is finite games? So finite games just means the game that is played for a limited number of time. Like they could play it for one time, like what we have seen so far, but also maybe for several rounds. I like you play several multiple rounds of rock, paper, scissors also. So that's is it for mixed strategy.